Thank you, Torsten. Good morning, everybody. Thanks for being here. It's wonderful to speak right after Thomas, that he fixed all the IT for me now. I hope I can do that, and it just works. Excellent. Thank you so much. So I also want to pick up where Christian left us. So Christian was asking what is next. And actually, as we now understand, the Alps infrastructure is a virtualized infrastructure. It's not a single computer, but it's a set of computers. So everybody can have their own computer. So he asked me for a name. I'm going to name my part of the computer Etzel, because that's my mountain that I like running up every week. So this is actually possible. We can deploy virtual clusters. We can deploy a small cluster on this machine that would just be for me. This is really the high-level summary of what Thomas means with the Alps infrastructure. It is a very large infrastructure with personalizable components. I'm going to talk about the AI component. But before doing this, I want to talk about a little bit how did we get here? How did we get, even as a society, to be here? Because I'm a professor, I will start at the very, very basics. Actually, I will start 2 million years ago at the Stone Age, okay? So bear with me, we'll go fast forward relatively soon. But in some sense, in human development, we started really with the material ages a long time ago. Then we went to Bronze and Iron Age. And many of my material scientist friends would say today, we're actually at the Silicon Age. And today we're moving into a brave new world of the silicon components. But actually, I want to do a slightly different detour here. Because if you ask historians, they don't necessarily go to Silicon Age. They go to manufacturing. So they go to the Roman technology. Then we could talk about medieval technology. We can talk about Renaissance. And we could talk about, no, this thing is still not really working, Industrial Revolution. And by the way, all of these pictures here are generated by AI. All of my slides are generated by AI diffusion models. So everything that's not obviously a photo, like the one in the background, is generated by AI. So I'm one of those people who could not live without this today. But now, actually, what happened a while ago, this is still disturbing. So what happened a while ago is that we entered the era of technology. And technology is what's driving us today. Many of you may still remember, or the older of you may still remember the atomic age, well, or the space age, which was the time when I was born, and then we entered the digital revolution. Yeah, I see some people who may or may not be alive at that time. We entered the digital revolution. This is something that is driving us until today. And now I need to click twice for every single thing here. And now we're going into the information age, and actually really twice for future speakers. And as Thomas alluded to, the data age. So many people talk about data is the oil of today. We really need data. All these machine learning models are trained with data and compute and algorithms, but it was really predominantly the availability of data. But I'm going to argue that this changes now. So we are actually at the end of the data age. And what is now happening? Where are we going? I claim that we're going to the age of computation. And I'm going to argue for the next 5 minutes, and then we go a little bit more into detail. What does that mean, the age of computation? Well, the age of computation is something that we all see witnessed by one of our partner companies. It's actually the company, if you look at the valuation, the market capitalization here, it's one of the companies that has had the fastest growth. It's not the largest company in history, but has the fastest growth in history. With this AI boom, you can see it was basically worth nothing in 2014 on this scale. Okay, it was worth something. But it exploded literally to be a $3 trillion company for a couple of weeks before it had multiple missed expectations by the stock market. And interestingly, these missed expectations was, well, the revenue only doubled. And then the stock market said, oh no, that's disappointing. Right? So this is where we are today. So this is what I want to make the point, that NVIDIA is a compute company, not a storage company. It's not a data company. Fundamentally, it's a compute company. They make compute accelerators. So let's go a little bit further. Let's go to one of the people who started ChatGPT, who you could argue is part of that big revolution that we are seeing, Sam Altman, the CEO of the company. So Sam tweeted in February that AI models are generating about 100 billion words per day. The total number of spoken words by humans is just 1,000 times more. And that was a couple of months ago. Today, AI models are generating many more words. So now, there's already a discrepancy of 1,000. Now, look at the written text. How much do we speak and how much do we write? In fact, we write much less than 1,000th of what we speak. So this means that today, models are already speaking more than the corpus that the models learned from is available. So this is going to be an interesting problem, because actually, if you ask now researchers who have foreseen this a while ago, we're going to run out of data. We're going to run out of human-generated data. We already ran out of high-quality data. Right? The internet is big, but not all of it is high quality, so that's already over. Companies are struggling to find high-quality data. There are even scientific articles on this. Oh, this is strange, it has a delay. There are even scientific articles on this in top-class machine learning conferences like ICML that predict very similar scaling laws of when are we going to run out of data. They talk specifically about LLM. We could now argue about multimodal. I'm also claiming we're running out of multimodal data given the deployments we have in compute capability. So what are we doing now? What's the next? How do we continue growing? Because Thomas wants to grow. We all want to grow. We all want to move forward with this compute field that's a major driver of humanity today. What do we do? Well, of course, we have these computers that can generate data. That's the next step. Actually, all the data challenges that Thomas talked about is not observation data. Much of that is generated data that comes out of our own simulations. We take observation data, we pump it up to a factor of 10,000 to a million more, and then we write it back to disk. All the data management challenges are simulation data, again, driven by compute. So now, synthetic data could even be real, or could even be better than real data. So that's something to think about. So now what do I mean with this age of computation? Well, if we actually go to human developments, for us as scientists, this is a scientific symposium, it's very interesting to think about, could we be replaced by an AI model? I believe maybe. I actually believe probably, to be honest. I have contact with AIs that are in preview in various companies, so this is quite interesting. So what can we do? Sakana Labs just published this paper, which was highly shown in Nature, that large language models can actually, well, with a lot of caveats, behave like a scientist. In fact, yesterday, OpenAI released, or today, depending on what time zone you're in, OpenAI released the strawberry model. The strawberry model bases on the fundamental idea of the model discussing with itself somehow. The model repeatedly invoking itself. And here's something that comes in, it was actually developed in my group at ETH Zurich, enabled by the Alps infrastructure, enabled by, or early versions of it, by the environment we have here, this recall graph of thoughts. And the idea is very similar. We invoke LLMs iteratively to solve complex tasks. We actually have teams of LLMs working together where LLM1, or AI1, LLM is just a science word for AI. LLM1 talks to LLM2, and in an argument they solve it. Like thoughts, like we have thoughts. Our thoughts are a way to argue with ourselves. Right? We are not language models. We are not language-generating machines. We think before we speak. These language models don't think before they speak. What the big news in the strawberry model is, it actually thinks before it speaks. Currently, you can output the thinking if you want. It's a whole lot of junk that it's like if you would read my thoughts, I have a whole lot of junk in my head, but I hopefully can control what I say. Right? So that's not true for all people, and not true for me always, but right now I think it's, well, maybe it's not true, as you can tell. But what I wanted to say is really, computation is the fundamental driver of our society. Computation is the new oil. Because we are running out of high-quality human-generated data. Computation is going to generate new data. We will use this new data together with more computation to drive the future of science, to drive the future of humanity, because science and insight has always driven the future of humanity. And now in my second part of my talk, after I argued for this age of computation, I want to argue how we can use scientific developments, or how we can drive scientific developments in that age of computation with a very particular use case. And the use case was already mentioned by Thomas. The use case is climate sciences, because it affects all of us. We want to understand the expected state of our atmosphere, the expected state of our Earth in, let's say, 30 years. And we may want to understand how we should behave today in order to change it. And climate sciences is fundamentally one of the most challenging simulations, or the climate problem that I have ever seen. I would claim it is the most challenging simulation, because the Earth system is very, very complex. The Earth has 511 million square kilometers. It's a pretty large simulation object, right? So now let me go a little bit more into detail of how we do climate simulations today. So the first thing we have to do in order to run any kind of computer program is we have to so-called discretize the Earth. We have to discretize our object of simulation. So at every couple of spatial resolution, in the spatial resolution, we have to put points, we have to represent the Earth by a set of numbers. And here comes the resolution in. So what is the distance between two of those numbers? So for example, here I range from 1,000 kilometers down to 100 meters. In 1,000 kilometers resolution, basically the country of Switzerland is represented by 4 numbers, which is not enough. At 100-meter resolution, the country of Switzerland is represented by 400,000 numbers already, right? So this is interesting. Now, what we do is, as we represent with more and more numbers, it's pretty obvious to everybody that we get more and more resolution, that we get better quality of the represented object, better simulation quality of this represented object. So we resolve more processes. Thomas has shown that video. And that video was really an indication of that in this 1.25 kilometer resolution, we resolved clouds. So actually clouds naturally emerged. And this is one of the major challenges in climate sciences. So you really need to understand how clouds behave, because clouds have a major impact on our Earth system. They reflect the sun, they rain down on us, they hail down on us, they snow down on us. And these are all things that we really want to consider to understand climate. But now if we work at 100 kilometer resolution, we would not be able to resolve clouds. If we now go finer grain to, let's say, to 25 kilometers, we can resolve very large cyclones, extremely large meteorological objects. So they are of partial interest, I would say. But really only at 1 kilometer resolution, as Thomas alluded to, we get rainstorm, we get relatively large storms resolved, or also smaller storms. If you want to resolve those little clouds that you see in the sky, you have to go to 100 meters, which is right now even is not dreamable for most of the scientists. Most of the scientists today dream of the 1 kilometer resolution. But now let us look a little bit at the data required to store one climate run, just one, for a 30-year time window. So I can do the 1,000 kilometer resolution in 500 megabytes. Well, this fits on my USB stick. In fact, even 100 kilometer fits on my USB stick, if I have a really, really expensive one. But if we go to 100-meter resolution, that would be 50 petabyte of storage I would require. That is, could be about 1 million USB sticks, depending on the size of your USB stick. Now, what you do in order to understand climate is actually, you have to really look into the future, and you cannot just look at a single scenario. Because what climate is the expectation of weather in the future. So it's what is the probability? So for example, if you talk about climate, in 30 years, we are not saying, well, it's going to rain on the Friday the 13th of 2054. Right? That's not how we talk about climate. We're talking about climate as in these 30 years, there's a certain probability of rain and a certain probability of sunshine. So what you need to do in order to get to the probabilities is you use so-called ensemble simulations. So you run multiple different scenarios to understand what the probability distribution in the future is. Of course, the more scenarios, the better of a sampling of the probability function you get. But let us here just look at the ensemble members. This is how many simulations we can run in one simulated year per day, like in this plot. So a single simulation is 10 to the 0, and then you have an exponential scale going up. So the first thing we realize is now, at the lower left, this is what I can do on my laptop. So I can run at a very coarse resolution, a very small number of samples. So that's very easy. And now as we are going towards the top right, I can either run more simulations or I can increase the resolution. So one of the two, if I get more compute power. So now we can look at specific machines. So we can look at this Levante machine, for example, which is at the German Computing Research Center. It's a computer dedicated to climate research. This can run a 5-kilometer model, global 5-kilometer model, in a single simulation. So that's not what we want, because I mentioned we wanted the 1-kilometer model. Well, now we can go to the LUMI system that Thomas mentioned. On this system, we can get to 2.5 kilometers, which is close. Or we can now look at the fastest supercomputers we have on the planet, which is the Frontier system or the Fugaku system. They're equally fast in that respect. They can go to 1.5 kilometers. But now, I'm not a climate scientist. I don't actually really understand what I'm talking about here at a very high level. But now, we had a meeting last year to understand what would it need with climate scientists, with real climate scientists. What would it need to compute the climate of the future globally for the Earth, but with a resolution that allows us to make local predictions? Because today we cannot do it. Today we can argue about, well, there will be a 1.5 degree or 2 degree average temperature increase on the Earth. But I don't care about average. I really care about what's happening in Zurich. Can we still live here, or are we going to melt down? The month of August was the hottest month on record since the beginning of measurement that we had. So it's getting a little bit interesting. But we had this meeting last year, and they said, the climate scientists, they said that's the target. So that's outside where we can compute. That's a little bit of a problem. So we need people like Thomas, we need the Alps infrastructure to move us towards that. But the Alps infrastructure is not going to get us there, unfortunately. But what can get us there, and it's all written in a paper if you care about the details, but what can get us there is, well, either have faster supercomputers, which is going to be hard because Thomas mentioned the Moore's law ends, so the only thing we can do is throw more energy at it and run bigger supercomputers. By the way, I really believe that in Switzerland, it would be of strategic importance to make energy cheaper and to really build an energy infrastructure that can lead us into the future. So this is an aspect of national importance to do this. But we can also play tricks, and these tricks are machine learning. So we can actually make the computation much more efficient on the machine learning side. And yeah, yours is getting nervous. Excellent. So here, this is again the meeting. There's Thomas in the middle, there's me somewhere on the side. And so we all met there and understood what it would take to run this. On the Alps machine, to run one run would be 37 days of the full machine, which is very, very expensive. And that would not get us to the full target that they had. Right? So keep that in mind. Okay, so now I can go, in my last 5 minutes, I can go a little bit more into the scientific details, what we could do to help the climate scientists to actually run these models. So they use a tool chain that goes from the observation data to the simulation, to the interpretation of the simulation data, to the final climate insight. So this tool chain is actually quite long and extremely expensive. This tool chain has data, this tool chain has compute, and it has models. And I don't have enough time to go into details of what this all means, but I want to entertain you a little bit with nice graphics and specific examples. So let's look at the observation data. This is data that we're collecting every day from satellite images. We have a lot of satellite data actually coming in at the terabyte per day rate. We collect it from sensors, like my watch actually measures the temperature, or better, my phone measures the temperature far away from my skin. And we have all these sensors, but unfortunately, these sensors are not equally distributed on the planet. So we have a lot of sensors, for example, in Western Europe. We have a lot of sensors in the United States. We have a lot of sensors in China. But where Thomas comes from, there are not many sensors, like in Southern Africa or Central Africa. So we have to do something to also gather as much quality data as we can from the sparse sensor data we have in order to fill a uniform grid across the planet that has the values over the ocean where there is no single sensor about as good as the values that is over Zurich where we have a ton of sensors. Right? So how do we do this? Well, one idea is to use diffusion. All of these pictures here, these two pictures, for example, they come out of AI models. These AI models use a technique that's called diffusion underlying to generate these pictures. And they can do really fancy stuff. I know this thing completely stopped working. Okay, so now let me give you a 2-minute summary how diffusion models actually work. So you'll learn something about AI today because I promised you AI. It's very, very simple. In a diffusion model, how you train it is you take an image, a real-world image, and you start adding random noise to it. You see at the very beginning there's kind of an image and then it noises. But what you learn is the opposite process. So you add noise, but you train a model that undoes the noise. Right? So after you added it, you know what you had, and the loss function is basically the difference. So it's super simple. And then if you run it, you can start from random noise, and you run it the opposite, and it'll generate you the image. Like this is the 5-minute version of how diffusion works. This is how all these images are generated. It's quite nice. So we can take an example. Ah, man, this is disturbing. I mean, for the next speakers, it's going to be a disaster. So we can take an example here, like this dog, and let's say I don't like this dog. I want to replace this dog by a yellow cat. I do exactly the same thing. So I have a mask in the middle where the dog is kind of marked as white. And then I start from a random image, but now I bias the random image with all the black data, which I have in the left one, but I leave the white data open. So now imagine all the black data that I'm using for biasing is my measurement data that I have from my observations, and I'm filling in all these places where I don't have measurement data with AI models. It's exactly the same thing. Here I'm filling a cat, but actually in meteorology or in climate science, I don't want to fill in the cat, I want to fill in the missing values. Very much the same principle, very much the same diffusion model. We can use all of these AI technologies. This is just one example. We have many, many, many examples in my group, how we can use AI models, and you can read this. There's a paper, blah, blah, blah. And I don't want to go into too much detail because I'm running out of time. We can now look at actually real meteorological data, and we can look at how the error behaves. So for example, the GraphCast forecast model is not so good in these areas. You see the redder or the bluer the worse. So the interpolation baseline is also not so good, but our diffusion model actually performs really, really well on real meteorological data. But I'm trying to more communicate the insight and not so much the specific values. You can go to the paper, which you see at the bottom, if you really want to understand this in detail. So I want to come to the end of my talk. I want to quickly summarize what I was basically trying to say. Really, computation is the new oil. For computation, we need two things. We need computers and energy. We have both of those here with the Alps system. The Alps system is one of the largest AI-capable infrastructures, the largest public AI-capable infrastructures worldwide. There are many, many private players who have more. Actually, I just read yesterday that Oracle is building mini nuclear power plants to power their next portable nuclear power plants, which is kind of crazy, to power their next system, or the system that's being deployed. Many others use also portable power plants these days. Energy is the future, so we really need a good strategy for energy. Fortunately, Switzerland is very three-dimensional, so we can actually have a lot of hydrological power plants here. We can use them as batteries, which is wonderful. When the energy pricing in Germany goes negative, we can take it and we can sell it back to them later. So that would be something we could do. It's a business model, but really we need our energy for compute. So then I talked about climate prediction, I talked about a data assimilation example, one of many, many examples. And then if you really care about this, there is a full version of this talk on YouTube where I give this talk, for 1 hour, and you get all the gory details of how the AI models work in case you're really interested. But at the end, what we want to do with the Alps system here is to provide easy access to climate information to everybody on the planet. Like, this is very important for us. We want to democratize access to climate data, and we're one of the leading figures in this consortium. So with that, I would like to end my talk, and in case you care about the full version, it's on YouTube. Thank you.